Look, I don't want to be here either. I'm just kidding. So for all of you who are panically sending me emails, it's fine. I got like 20 emails. Like, hey, there's not a quiz today, is there? It's not ever a quiz. Like, I just use it as a threat, okay? I really don't want to take up time with policy in this class. But if you guys' attendance drops, I'm not going to be happy with that. But now I understand all of you out there in TV land who couldn't make it today. I mean, if they didn't plow my street, I wouldn't do it again. So, that's why we have videos. So, anyway, I'm glad so many of you actually did manage to make it in. I'll probably be quick today. It is a snow day after all. Actually surprised that they closed campus until 10 a.m. and that was it. Actually, where I went to college, the University of North Carolina at Chapel Hill, my undergrad, pretty similar place as this. They actually pride themselves on the fact that they only closed once for the Civil War. That's not a joke. It is a joke. It's called the War of Northern Aggression is what we call it there. So anyways, it doesn't snow in North Carolina, right? So anyway, so I'll be quick. Why don't we end a little early today? Because why not? Why not? So, and I've been holding you kind of late almost every day anyway. I apologize for that. I shouldn't be doing that. Let's see. Homework's due Wednesday. One more problem set. You have that extra Friday to ask me questions. Oh, I'll send a doodle poll. It sounded like to me you were overwhelmingly in favor of having the review Wednesday. 2 Fridays from now you have a test, right? Your first test. Wednesday before we'll do the review. I'll send a doodle poll, but I mean it was kind of obvious that's what you wanted. That's what we're going to do. So I may have a double lecture on Friday as a result. And anyway, Wednesday I'll be very clear what's on the test. I will also send you the cheat sheet. I don't know why, but all my students, ever since I taught this class the first time, everyone was like, please send us the cheat sheet the day before. Or, well, I'll send it to you on Wednesday. I don't know why, but I mean, whatever. If you want it, I'll send it. Now, I have to put up the caveat that I may change it, because sometimes if I'm not completely done with the test, or if I've made a mistake, I may change the cheat sheet because you need it, because there's something that you need that's not on there. So I may alter it. Usually I don't. I've only screwed up once or twice, so... Anyway, all right, so no big deal, same old, same old. And today we're going to get into a little bit harder stuff, and I'm going to make it a little, hopefully, as clear as possible. Can you see all right? Hopefully I'll make it a little bit more clear exactly how all of this, all the equations tie together. So today I'm going to talk about our 48 equations that we have, and hopefully I'll make it as clear as possible. As in all things, let's review everything we've gone over from the very beginning. Don't forget that internal energy is 1/2 RT times degrees of freedom. Sorry, I don't want to write it all out. It's hurting my wrist. So don't forget that. And then so that's U, and then we can have the change in U. And the change in U is the change in heat plus the change in work that is done. If you're at constant T, at constant temperature, because of the first thing, all right, so we need to start by this, we need to start by this. Now you're starting to see, hopefully, I said this before, hopefully you're seeing how you remember these things with stars, they lead to other things. If U is a function of temperature, and if I hold temperature constant, therefore the change in U is 0. And when I say a gas expands, a gas contracts at constant temperature, and I'm going to have to tell you that. I can't be cutesy about this. If this is the case, then you automatically have this. The heat is minus the change in work, which was part of actually I think this present homework, or maybe it's the last one. And also work is, let's see, let's do work. If it's reversible, I'll just write it underneath here. We got minus nRT, natural log, BF over BI. Okay, that would be reversible. And irreversible, here I'll just write that real quick. Oh, sorry. Again, my symbology is bad. I need to be integrating it. And I know that work is always exterior pressure times the change in volume. And reversible, the exterior pressure is the interior pressure. That's how you pick up that MRT, natural log bit. But if not, you get the easier case actually. And again, I will be very explicit. Okay, one of the things to look out for in terms of, interval. One of the things to look out for me in terms of things I like to do is when, just to be clever and cutesy, when I have irreversible transitions, what I have is I have the piston expander contract such that I'll say like a piston expands in a room full of people. All right, a room full of people is at atmospheric pressure. So one of the things to look out for me when I do irreversible is that I will always have the piston expander contract to whatever the exterior pressure is. So I'm going to feed you that, but I'm going to do it in kind of a cutesy way. So anyway, look out for me when I do that. You're going to have a lot of these questions on the next problem set and plenty on the test too. Let's see, what else do we want to do? If we are at constant V, if we do constant volume, then there can be no work, and that means that the change in U has to be all the change in heat. Now, of course, again, I have to feed that to you, just like I did on the problem set. 100 joules of energy is supplied to the matched piston. I have to tell you that. It makes it kind of boring, but whatever. But at constant, I'm kind of going in the wrong order. At constant pressure, I showed that the change in enthalpy is the change in heat. Again, being the most common. And of course, let me define enthalpy as a Legendre transform. Remember that U has a natural dependence. So remember, that's not a mathematical thing. It's a thermo thing that U, I know that U has a volume dependence because work is the change in volume and change in U is the change in work. But I don't like that necessarily. Sometimes I want pressure to be the thing that I want energy function to be a function of. In which case I do the Legendre transform. I subtract from my function that is a function of volume, and I don't like that. So I subtract V times its conjugate, which is minus P, or plus PD. So don't forget that. And then look at the change in H, look at the change in U, the change in PV. You know, PV are often going to change together, so that gives me a bit of a nightmare of a situation. So what I'll do is I'll take that change in U plus the change and our change in PV. There you go. So anyway, a bunch of homework questions just right there. Also at constant temperature, therefore at, right, OCD. Therefore, at constant T, OCD, that is me, constant T, the change in H is also 0. Oh, I need to put units down. All right, it's constant point anyway. Okay, well, now remember, we're going to get into it today, but today I'm going to start to introduce all of the 48 variables. You already see a bunch of stuff up here. Oh, let's see. Sorry. Got to start there. From here, we get this from here, and this from there, so I don't need a star. I think that's all the stars with you. Anyway, sorry about that. Okay. Now I promise that we're going to get into some harder stuff today. So this is just a review. But we were talking about heat and heat capacity. So let me finish up our discussion on heat capacity. I mean, you're always just, oh God, there's another thing I meant to tell you. You got to be careful. And I didn't explain this last time. I kept reminding myself to explain this. Excuse me. Heat capacity is extensive. Right, so I'm going to give you a heat capacity per mole because that's how you find it in data tables, but you must multiply it by the number of moles. And this is going to have units of joules per K mole. All right, but that's not the real heat capacity, it's the molar heat capacity. Heat capacity of a cup of water is much greater than the heat capacity of the ocean. That's rather obvious. So look out for that. So whenever I give you the heat capacity, whether it's constant volume or constant pressure, I'll give it to you per mole, which is how I find it in the back of the book on the data tables. Make certain to multiply it by a number of moles, and don't forget that heat capacity at constant pressure is not going to come up a lot because I just kind of choose not to. I try not to make your lives 2 terrible times delta. Oh, I should integrate it, sorry. Again, not, whatever, it doesn't matter. Anyway. So again, we have heat capacity at constant pressure, which is greater than heat capacity at constant volume, which is the thing we're going to prove right now. Don't forget that I'm going to supply you with a certain delta, a capital Greek D, delta Q. And from that, I've given you the moles, I've given you this, and from this you get your temperature change. And from there you get U, you get H, and all that jazz. So anyway, just another little factoid. I think I forgot to mention that last time. It's on your homework as well. Okay, so I think I need to use a new board. Any guys in here were circuit guy? No one's in that class? I told them several times to erase the board. But anyway, sorry, I'm just playing. Okay, so last time I mentioned that heat capacity at constant pressure is greater by a factor of R, or actually NR. It has to be NR because R has units of joules per K per mole, and CV or CP have units of joules per K. So therefore I have to multiply, this difference again is NR, and that makes the unit works. And I just told you that, and you accept it, but you shouldn't do that. All right, so we're going to actually prove this exactly. And this is the kind of thing, this will probably be about the hardest part of this class, is doing exactly these kinds of proofs. So we're going to spend about the next 2 weeks doing nothing but these kinds of proofs. So get used to them. As I mentioned last time, in that extra hour, I will always help you set up the question correctly, because how you set these up obviously matters. So I'll set it up for you, and then you're going to do maybe at most 3 steps on your test. On your test, no more than 3 or 4 steps, and that will be the answer. You get to 4 steps, and you're not at the answer, you're doing it wrong, stop, do the easier questions, and then come back, right? Because you're doing it wrong. So don't forget that. Now this one's a little bit of a tough nut to crack. Okay, so I know that change in H, change in temperature, constant pressure is CP, oops, and I'm going to subtract from that CV, which is du, dt, and constant V. Okay. Now I think, no, I didn't put this on the homework, but here's the next thing. And again, I think that back in the day, back in like the 1880s, to be blunt, this was all known around the 1880s, I think that they knew the answer and they were able to like reverse engineer these types of derivations. I think that's how it worked. I don't really know, I wasn't there, I'm not that old. Okay, H is the change in U plus PV. And don't let this freak you out. You know how to deal with this. This is not unknown to you. And of course, this is CB. Okay, now again, you're used to, this is like x squared plus 1/2 x, the derivative of. And that's not hard. That's not difficult at all to deal with. You're just not used to not having x's and y's. So you deal with this just like you always deal with it. You split it up. So it's going to be a change in U. Sorry, I'm fearful that some of you can't see this here. Okay, I'm going to break it up. B. And just like I did with change in H, like I dealt with this before, this is going to be P, change in volume with respect to temperature and constant pressure, plus volume, change in pressure with respect to temperature at constant pressure. Doesn't amount to much. Change in U, change in T at constant V. Okay, very easy. Now I can get rid of a term. We did this last time. What term can I get rid of? Yeah, right, dP. All right, we're at constant pressure. There is no change in pressure. Temperature changes, but that doesn't matter. This is 0. So remember, a lot of things are going to be 0 or 1. Expect that a lot in these proofs. Okay, so now I'm left with change in U with respect to temperature at constant pressure, and I did this last time, plus P dV dt, which is very easy at constant pressure. One of those times that what's held constant actually does not matter, minus the change in U with respect to temperature at constant volume. Okay, I did this on the extra hour on Friday, but I need to do it again. I kind of jumped the gun. I actually kind of wish I hadn't done this, but I'm kind of at a sticking point. All right, now this I can do for a perfect gas. This isn't particularly difficult. In fact, I think he did dV dt at constant P on the first homework. That's with the van der Waals equation. And I'll be nice, I'll just make it perfect gas. So this guy I can see is not a problem. That is heat capacity and constant volume. That's not a problem. I can look at that up. That guy's a problem. I'm not sure what that is. Well, I actually already know what it is, but whatever else probably. But now, this is a time, and again, you're going to kind of roll your eyes at this. I'm going to stop the derivation to do a different derivation and then go back to this. And it's just the easiest way. I don't really have much of a choice about this. So sorry about that. So the point is that I want to connect this guy, and I think it has a relationship because it's the same as that guy. And to do that, again, I happen to know that I want to expand the change in U. I want to expand this, and I'm going to force it into this shape on the left, and whatever's on the right is on the right. I just let it be. It's going to be what it's going to be as long as I do it correctly. Now I've got to choose the variables I want to expand it. And in this case, let me cheat and look at the answer. Let's see, I'm going to want to do, I'm going to do pressure and temperature. I choose to do pressure and temperature. Okay, so let's let you change the temperature and your whole pressure constant. Yeah, I'm doing that right. Sorry to cheat like this, but what can I do? Now, as soon as I've done this, as soon as I put that letter there, the next term writes itself. One of the few rules you have to follow. I'm going to have to expand in terms of pressure now, because that's there. Now, of course, I'm going to hold temperature constant because that's there. Again, you see that it's very, very simple. There's just a handful of rules you've got to know when you write these suckers down. And again, on the test, when you have to do this, I'm going to point you in the right direction. Because there's too many ways to start this, which you saw last Friday. Some of them lead you to the answer, like what I'm doing now, and some of them don't. So, and I don't expect you to be able to figure that out very easily. Not now. Go to grad school. Gravy train ends. Okay? Now I'm going to multiply everything by 1 over the change in t. Again, because that's just a simple algebraic rule that I can follow. I hope that doesn't, sorry, I know I've been screwing this up. I know it looks a little messy. Let me rewrite that. That doesn't kill you. Okay, so I can certainly multiply by 1 over the change in temperature. Why not? I can do whatever I feel like, as long as I follow algebra's rules. Now I'm obliged to make something constant, and what I'm going to do is I'm going to make volume constant, and that gives me this guy here. And again, there's nothing that says that, oh, you can't do that, or you can't do that, or you have to do that. It's whatever I choose to do. I do it. It's just, of course, I choose to do things that gives me the answer. So, again, I'm cheating. Okay, so this is 1. And this guy, we did this last Friday. Spot it. Remember I just said, so everything's a 0 or a 1. 1 or 0? 0. 0. Why?
Constant volume.
No. Constant temperature. Constant temperature, right. Constant temperature means the change in U is 0. Right, equal partition there. So this goes to 0. And therefore, change in U, respect to T. Remember we did this last Friday. It doesn't matter, I'm doing it right now. Okay, they're equal. And again, remember I said that this is the path independence of U kind of showing up. Now, notice I didn't engineer this. I didn't make it work. I didn't set it up from the very beginning to come out this way. The great hawk that I followed did it, you know. So, yeah, I just followed nature's rules, and nature's rules says, yeah, I told you it's path independent, dumbass. And sure enough, that comes right out without me having to do anything except getting it right. So, okay, so that means that this guy, here, it bears rewriting, CP minus CB. All right, I'm going to look here, and obviously these two are canceled out, is P, dV dt, constant pressure. Now, again, I will be very friendly, and I will do perfect gas. Let's do perfect gas. Sorry, again, a little bit of an aside. V is nRT over T. Folks, I'm not even going to bother to do the derivative. It's quite obvious that this is P from here, nRT, nR, my bad, Maxie, I almost screwed up. The T is gone. And again, I'm not going to do that derivative. There you go. That's the difference. Very, 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 very easy. And I'll rewrite that right here just for the whole. One last layer where CP is equal to CB plus NR. Okay, another way, I put that slightly differently before. I just like to put things multiple ways, so it kind of, I think it helps stick in your head. When you see the same thing done differently, it helps. So, anyway, yada, yada, yada. Could very well, oh, I'm thinking about the test already. Extra credit question. The last extra credit question is always number 13. 13 or 15, I can't remember. And I may ask you something this hard. This would be as hard as it gets. It's extra credit, anything goes. Now normally throughout the remainder of the test, I will not ask you a question this hard. I'm not going to go there. This is way too many steps, and I don't want you even trying to memorize it because that's stupid. It's just not going to get you anywhere. But if I feel like being a real I might have this as the extra credit question. Again, this is as hard as it's going to get. So, anyway, I don't really have anything else to say there. I'm not ending class. I'm not. All right. I'll leave a couple minutes early, all right? But I do have to get to the material to help you answer questions 9 and 10 because I haven't gone there yet. But mostly I want you to kind of step back and see. I'm going to get into the whole 48 equation things. I'm going to write them all down. And you're going to kind of start to figure this out. Now notice that let's see, last Wednesday I was talking about the metal, the magical metal piston, and how you compress a gas. You kind of know that it wants to get hot, you're right. You know it wants to get hot, but it's made of metal, so it'll shed the heat. And so the work you do, especially in compressions are easy to understand. Expansion's not so much, but a compression is very easy. I know the thing wants to get hot, but I said it's isothermal because I said it. I don't know why, but it is, but it's because I decided that. The heat gets shed, and the temperature stays the same. Now, remember, of course, if I compress, it's going to get hot. The heat will shed. That's dQ is negative. Is that right? Is that right? One of the times I'm not tricky. That's right. Q is negative, and if I touch it, it feels hot. And that's the answer to one of your homework questions, by the way. Or the opposite. I don't quite remember what I did this year. Okay, so that is how we keep things isothermal in, a process in a metal sphere. However, notice that this was a bit of a subtlety, and we started talking about all this heat capacity stuff. I was talking about, especially on your homework, heat goes in and the thing gets hot. Well, why didn't it shed the heat? Because it wasn't isothermal, because it was wrapped, the magical cylinder, or the power plant in your homework, was wrapped in glass wool. That's thermally insulated. That's why I can add heat, and I can add heat to my magic cylinder. This is actually how it works. I actually had devices in my old lab that work this way. If you need to impart heat to something, and yet you still want it to be thermally isolated, which, why would you heat something if you wanted just to shed heat? That doesn't make a lot of sense. What you do is you actually take the magic cylinder, and you're going to wrap it with just wire, and then you spray insulating foam on it. It's literally it's like a fire extinguisher. You just spray it on. And then all you do is you add current. Add current, and either it's going to heat inductively, which is just a fancy word for adding current, or literally it just gets white hot. It gets jacked into the wall. So anyway, notice that though it requires insulation. So I didn't tell you this, but I've actually secretly been doing a different condition than I've really talked about, and that's adiabatic. Okay, so in the big picture of things, I'm going to say this and I'll write it down in a minute, so don't write this down because I'm going to write it down in a minute. We have two themes, essentially, to thermo. One is isothermal, as I've been yakking about, and the other one is wrapped in glass wool, which is adiabatic. So we have these two themes. Within the two themes are two ways. That's reversible and irreversible, giving us 4 different things. Between these 4 different things, I've got about 12 variables. 12 times 4 is 49, right? So that's 48. This is 48 things. Right, so let me write this down. So this is thermally insulated. And that means wrapped in glass wool. And so anyway, let me try to make a big picture here. So I've got isothermal I'm leaving some space up here, by the way, just look out for that. Adiabatic. All right, then I've got ways of doing things, which is irreversible and reversible. Okay, now, the way that these work is that you pair them in 4 different ways. Here and here. Okay, so we can have adiabatic irreversible, adiabatic reversible, which is all the things we're going to talk about today. I've done isothermal, irreversible, and reversible. I've already done it. So, what are all the variables that we have? So, again, we heard this for a reason. Let's see, we talked about U first. Then we had heat, we had work. We had, okay, you know, I always deal with gases, so I've got pressure, volume, temperature. I'll leave out moles because I always keep systems closed. Enthalpy, of course, with enthalpy, we learned about heat capacity, constant pressure, but don't forget heat capacity, constant volume. What we're getting into next week is S, entropy. When I introduce entropy, I can introduce A, which is a form of enthalpy, essentially. Actually, it's kind of an alternative to this guy, G gives energy, times 1, 2, 3, 4, times 4, 48. I warned you, 48 equations, you cannot remember them. So stick with me in my little stars, all right? My little stars, you're going to only have to remember about maybe 10 things. At most, 10 things at most. And even those 10 things are on the freaking cheat sheet, okay? And trust me, you'll see it. You're going to see it in a week. So even if you don't remember them, you have them, right? You can load your actually. So I'm this old. Actually, calculators. The TI-85 was the first real graphing calculator that became available just my junior year when I was taking this exact same class, using the same notes, by the way. And I thought I was very clever because I had a programming function, and I programmed in all 48 equations. And I knew I was cheating. I kind of was. According to the guy's rules, he said not to do that, but I did it anyway. But God, that's the worst story I could ever tell, isn't it? But I didn't look at it. For one, as in the test, I was like, no, this is wrong. Number 2, I didn't need to look at them. I remembered them at that one because I had painstakingly typed them all into my calculator. So I didn't need to look at them. So anyway, okay, well, I'm just blathering on. So note that there really aren't quite 48 because when you're isothermal, reversible, or irreversible, the change in U is 0. The change in H is right because they are path independent, right? And so these are like paths, and then these are kind of like halides. I don't know how to describe it better. So you can eliminate some of them. Basically, yeah, any of the ones that are path independent, if you're isothermal or adiabatic, so again, U's and H's are going to be the same, whether we're this way or this way. They are different than when they're adiabatic, but we're covering that right now. So that's a whole point. Okay, adiabatic. So I'm hoping now you see the big picture. And by the way, this whole time I've been talking about adding heat. Your homework, technically I was adiabatic. I just didn't want to complicate things. First thing to do, okay, this gets a star. I'll put it right here. Okay. And I need to add a little unit. I should integrate it technically, whatever, it doesn't matter. All right, now this is one of the bigger things. Now you engineers, I'm sorry chemists, but the engineers actually have this right. So us in chemistry, we define heat as only that which is transacted between the system and surroundings. It's not fully correct. Because that's like to say, if I wrap something in glass wool, all of a sudden the heat inside of it, and it does have heat, the magic cylinder now wrapped in glass wool, there's still temperature inside of it. It still has, it didn't suddenly freeze just because I wrapped it in glass wool. And that's actually horribly important when it comes to some of these conditions. Engineers describe this correctly, chemists don't. Because to say that it is so narrow that heat can only be that which is transacted from system and surroundings is not correct. So again, because it ignores the fact that just because I wrap a cylinder, it's got a gas, it's at room temperature, that temperature's still there. That temperature can be used to instigate changes in said system, whether it's wrapped in glass wool or not. It's irrelevant. So anyway, so look out for this. So now again, homework. Next homework. A gas expands adiabatically. Write this down instantly. There you go. You already got a point. I'll probably ask roughly 10 different things. Well, you see, you got 12. So generally, I'll ask about 10 of them. You just got one. 10%. That's totally enough. Anyway, so sorry about that. Now again, no star here because I don't need a star. I know that the change in internal energy is now the change in work. Now I just got to define the change in work, and that's going to be a bit of a Bismarcker. So it turns out, when it comes to adiabatic, let me. This is always kind of a real pain in the ass. Whenever I do an adiabatic and I say, okay, a gas expands, a gas contracts adiabatically, I can just go ahead and preview. I'm going to prove it in a second. I'm going to go ahead and preview. You got to get the change in temperature. Right, so I've compressed the gas adiabatically, it got hot. I expanded the gas adiabatically, it got cold. There's going to be a temperature change. Temperature change is everything when it comes to adiabatic. You're going to get the change in U from the temperature change. The change in U gives you the work. And then you've got H, and then you've got these other things that are coming up anyway. So, when it comes to these two guys, by the way, again, I'll give you the per molar, and I'm going to say, hey, tell me what CP and CV are. And that's a clue. Multiply them by another molar. Anyway, why am I talking about that? Let's do this graphically. I like to do things graphically when I can, because someone can kind of figure things out that way. And like the maximum negative work deal about reversible, that was easily proved with the graph. All right, let's do an expansion, because I don't talk enough about expansions. So we're going to go from V1, T1 to V2, T2. Now, of course, I've drawn the temperature going down, which will happen, even if it's hydrogen or helium. Adiabatic, even hydrogen and helium get cold. And so there's going to be some change in U as a result. And, but you already said it was work. Well, it's not that easy. Oh, isn't it just minus P exterior dV? No, not necessarily, because I got temperature changing too. See, that's a problem with our old definitions of work, is that temperature is changing. And temperature and volume are going to change, and guess what? So is the pressure going to change. So I have pressure, volume, and temperature all simultaneously changing when I compress a gas in glass wool. Or expand. Expand is going to get cool, it's going to get bigger, and my definition of work doesn't necessarily apply anymore, what I had before. So here's how you're going to do it. All right, for one, again, like my point being, this is too hard. I don't know how to address this directly. As I have drawn it here, I've got pressure, temperature, and I didn't even put pressure on there, but I got pressure, temperature, and volume changing simultaneously. That's a real Bismarcker. But U is exact. I can do this. Change in U1, change in U2. And so the total change in U is the sum of the two. And I know that this is exact, and it's perfect. Okay, now one of them is very easy. So I'll put a little X there for like an intermediate state. It doesn't really exist. So I didn't really do the transition this way, but use exact so I can pretend. I can pretend that I expanded the gas, the magic cylinder wrapped in glass wool. The magic cylinder was expanded, but I magically did not let temperature change. I can do that. I have powers. I have strange powers. But anyway, so I allowed the gas to expand without changing temperature, and then my will be done. I then let it cool at a constant volume. Okay, first step, expansion, the temperature didn't change. Right, 0 joules. Joules, constant temperature. Okay, step 2. Step 2 is relatively easy. It's a constant volume temperature change.
Heat capacity.
Constant constant volume temperature changes are calculated how? What's the energy to change the temperature at constant volume? CVT. Again, I'm going to be in partial form. So, CVT. Okay. There we go. So I've given you a cylinder. I've told you its volume. I've told you how much I've compressed it. I have to tell you some things, obviously, or the questions are unworkable. I've told you the gas. I've told you its heat capacity, constant volume. But I didn't tell you the temperature. You're not there yet. Again, remember, I previewed. You have to get the change in temperature. You must get this. Because then, once you get that, you get the change in U. Oh, and then you get the change in work. The heat is 0, we already have that. And then, of course, you're going to do the change in U plus NR change in T will be H. And then next week, we're going to do these last 3. And bam, there you go. You got your 10 points. Okay, so here's how you actually do this trick. This is equal to the work. And just because the cylinder is wrapped in this magic glass wool does not mean that work is still not this. It is still this. That didn't magically go away. It's still exterior pressure times the change in volume. Now, this isn't a biz knocker enough. Now you've got 2 different external pressures. You've got either irreversible, in which case this doesn't change. It actually makes the question significantly harder to solve, by the way, just pointing that out. We'll do it next week. Or exterior pressure is interior pressure, meaning that you're doing it reversibly. The adiabatic transition occurs reversible or irreversible. If it's reversible, then this will become the interior pressure, and it gets a little complicated, which actually I will do right now in the next 5 minutes, and then we'll cut out early after we do this. Okay, now, here, I'll go right over here. I'm going to do, by the way, I've got a couple of handouts if you haven't seen them, just on like equipartition theorem. Anyway, check that. I see. Someone's getting a special test on Friday. Okay. Yeah, I don't have it. I have a cell phone, but I only use it when I travel. Your generation, you're slaves to those things. I was kind of glad that I was born without the internet. I'm not a slave to it. At the same time, it sure is convenient. But anyway, okay. So what do I want to do here? Okay, if reversible. Okay, so again, I can't. Sorry, my mind is kind of back in cats today because I'm buying a cat next week anyway. So. The reason I was saying, sorry, let me do irreversible. The reason I was saying about handouts is that when it comes to adiabatic reversible transitions, maybe not today, but on Wednesday, I'm going to put a handout on how to do it, how to do the calculations and all the work and heat and U and H and all that, because unfortunately, it's really kind of badly complicated. So what I'm going to do is I'm going to tell you what the exterior pressure is, change in volume, and of course that's going to be heat capacity times change in temperature. The problem is that I have one equation and 2 unknowns. I've got a final temperature. Of course I have to set it up. I have to give you the initial temperature. I have to give you the initial volume. I probably have to give you the final volume or something. Anyway, so I have to do certain things to set up the question, but you're going to run into the problem of the fact that you have, again, too many things changing in only one equation to solve it. Right? If I don't know x and y, then I can't solve. That's an equation that's unsolvable. All right, the answer is that you can cast change in temperature using PV equals nRT. You can cast a change in temperature as a change in volume. And therefore, you've got initial volume, and then you've got final volume being unknown, and now I've got one equation and one unknown. All right, you see what I'm saying there? Again, all right, let me do it for volume. I can express temperature, a change in volume as a change in temperature. I can do this because V is nRT over P. I've given you everything you need to know. Now you've got change in V as a function of change in temperature. Now you've got one equation and one unknown, change in temperature. It can be solved. It's a real pain in the ass, in all honesty. Wait for the handout, you'll see how it's done. I'm going to ask you some questions. It's not that bad. All right, let's do reversal. Okay, in which case, and let me do it as in partial form. Because you can imagine I'm going to do an interval. And yeah, just give me a couple of minutes and then we'll end a little early today. I feel like going myself. Okay. Anyway, OCD. Okay, now, so you can imagine, again, it's not the same problem. I've got too many things changing at once. Oh, and guess what? P is nRT, change in V over V. There you go. All right, just perfect gas law. There's nothing too hard about this. Okay, now I see that I got a bit of a problem that you got to get your variables either to the left or to the right. So minus nR dV over V is CV, change in T over V. Looks like I've got a self-similar equation. Now I need to integrate because again partials have no meaning unless they're integrated or divided by other partials. And of course I'm going to start at the initial volume, I'll end on the final volume, and that results in a temperature change from the initial temperature change to the final temperature change. And again, looks kind of ugly. OCD, there we go. Okay, I've got that. Okay, integral of 1 over x. Natural log. Okay, so I've got minus n r, the natural log. Natural log of a minus natural log of b is natural log of v over b. That's right. Vf over vi is CV ln Tf over Ti. Now, as I go further with this, there's lots of ways you can actually solve this. Let me be certain I stick with the standard way. Sorry, you see, I think I pretty much do this without notes. Okay. Minus ln A over B is equal to ln B over A. That's right. So, what I'm going to do is I'm going to bite this. Actually, I'm going to do 2 steps. Bi over Bf is minus. No, I'm eating the minus sign, so CV over nR ln Tf over Ti. Here, let me write that down. Minus. Here, let me write down the proofs. ln A minus ln B. Now remember, if you get stuck, if I ask you this on the test, then you plug this into your calculator because you kind of remember it, but you're not sure. So you plug the numbers into your calculator. Remember, always use odd numbers like 3, 5, and 7. Because 1s and 2s do weird things. 2 plus 2 is 2 squared. That's kind of a screw up. So anyway, so those are the proofs I used. And now here's another one. A ln B is ln what?
B raised to the A power.
Yeah, B to the A power. Okay, so now I can swallow this guy up. Yeah. I know this gets a little funky. Tf over Ti. Sorry, my handwriting is not CV over nR. Sorry, my handwriting is not so great today. That's not so bad. Okay, now here's a trick. Here's a trick, folks. I don't like teaching tricks, even if it makes the question harder. Notice that I'm going to give you the heat capacity per mole, and then you're going to multiply it by N to get the real CV, and then you divide by nR. Well, you could have actually just used the heat capacity per mole and divide by R. Just pointing that out. It's a nice little trick. Anyway, but I don't like teaching tricks. Okay, now here's a good one. Natural log of A is equal to the natural log of, very simple. The natural log of A is equal to the natural log of A. Right. These guys got to be equal. ln A is equal to ln A. Therefore, I to the CV over NR. Or remember that there's a little trick we can do here if you feel like it. There you go. And that's it. So, now the point of this is, let me make sure we got it right. So, the point of this is that when I ask an adiabatic, I say, you know, gas expands, gas contracts, it's adiabatic, I have to give you enough information to answer the questions, and I will. I sit there and do it myself. I don't just write questions. When I write your homework, I just don't write questions. I actually do it immediately after writing the question, make sure I can actually answer it. So I will give you enough to fill this out. And from this, you're almost always going to want to get TF. I had to have given you the rest of it. I gave you this, gave you this, gave you this, gave you that, gave you that, gave you that. I gave it to you. It's in there. Maybe it's a little hidden, but it's there. And from this, you're going to get TF. Now you got delta T. Now you got delta T, and then you can do the change in U. The change in U is going to be CV delta T. And that's going to be the change in work. And then the change in enthalpy, change in H, will be the change in U, which is CV, so let's integrate it. Let's integrate it all, CV delta T. And this, of course, is NR, oops, sorry, I don't know why I did that, NR delta T. Now notice something kind of neat here, CV delta T, because this will be on your next homework, it'll be on the test at some point. CV plus NR? CP. CP, PT. Notice that the pressure wasn't held constant. If I'm going to compress a gas, and I'm going to wrap it up in glass wool, or really no matter what, I change the pressure. Pressure is not constant. Volume is not constant yet. I use the constant volume heat capacity to get the change in U, and I can use the constant pressure. Even though neither is actually true, it doesn't matter. I can use the heat capacity, constant pressure to get the change in H. Okay, well, folks, I promised we'd end a little early today, so here's 1 minute early. And I'll have the video posted by the end of the day.